Vector spaces aren't just arrows or columns of numbers. This, a 3 by 3 matrix, is also a vector. The space of all 3 by 3 matrices has exactly 9 dimensions, 9 basis matrices, 9 degrees of freedom. Matrices form vector spaces, and once that's clear, an elegant formula falls right out, one that reveals exactly how any two subspaces fit together inside a larger space. Let's build this from scratch. Call M the set of all 3 by 3 matrices with real entries. A vector space needs closure under addition and scalar multiplication. If we add two 3 by 3 matrices entry by entry, the result is another 3 by 3 matrix. If we multiply one by a scalar, we still get a 3 by 3 matrix. M satisfies all the vector space axioms, so M is indeed a vector space. One critical point: matrix multiplication plays no role here. It is an extra operation that matrices happen to have, but it is completely irrelevant to the vector space structure. Now, to find the dimension, we need a basis. Consider the 9 matrices E11 through E33, where Eij has a single 1 in row I, column j, and the zeros everywhere else. Every 3 by 3 matrix can be written as a unique linear combination of these 9 matrices. For example, a matrix with entry Aij in position ij equals the sum of Aij times Eij over all I and j. Since we have 9 linearly independent basis vectors, the dimension of M equals 9. In other words, M is just R9 wearing a square costume. The same 9 degrees of freedom, simply arranged in a grid instead of a column. Now let's look at a subspace. Let S be the set of all 3 by 3 symmetric matrices where A transpose equals A. This means that the entry in row I, column j equals the entry in row j, column I. First, let's confirm S is a subspace. Adding two symmetric matrices gives a symmetric matrix, since the transpose of A plus B equals A transpose plus B transpose, which equals A plus B. Similarly, scalar multiples of symmetric matrices stay symmetric. So S is indeed a subspace of M. Now, to find its dimension, we count the number of free entries in a generic symmetric matrix. Consider a 3 by 3 matrix with entries Aij. The 3 diagonal entries, A11, A22, and A33, are completely free. The 3 above diagonal entries, A12, A13, and A23, are also free. But the 3 below diagonal entries, A21, A31, and A32, are forced. Each one must mirror its partner above the diagonal. So A21 equals A12, A31 equals A13, and A32 equals A23. That gives us 3 plus 3 equals 6 independent entries, so the dimension of S equals 6. Here's one subtlety worth noting. Only 3 of M's 9 standard basis matrices are themselves symmetric, namely the diagonal ones, E11, E22, and E33. But basis for S needs 6 vectors, so most of them won't come from M's standard basis. We need to construct new basis vectors like E12 plus E21 to capture the off-diagonal symmetric structure. Next, let U be the set of all 3 by 3 upper triangular matrices, meaning every entry below the main diagonal is 0. Adding 2 upper triangular matrices preserves the zeros below the diagonal, and scalar multiples do too, so U is a subspace of M. Now let's count the free entries. On the diagonal, we have A11, A22, and A33. That's 3 free entries. Above the diagonal, we have A12, A13, and A23, another 3 free entries. The 3 entries below the diagonal are all locked at 0. So that gives us 6 free entries in total, which means the dimension of U equals 6, the same as S. Here's an interesting structural point. 6 of M's 9 standard basis matrices, Eij, happen to be upper triangular, specifically those where I is less than or equal to j. These are E11, E12, E13, E22, E23, and E33. So in this case, M's standard basis actually does contain a basis for U. But remember, that's a structural coincidence, not a general rule. We saw that it did not work that way for the symmetric subspace S. A matrix that belongs to both S and U must be symmetric and upper triangular at the same time. Let's start with a generic 3x3 matrix with all 9 entries labeled. First, we apply the upper triangular constraint. Being upper triangular forces all entries below the diagonal to be 0, so A21, A31, and A32 all equal 0. Next, we apply the symmetry constraint. Since the matrix must also be symmetric, each entry must equal its mirror across the diagonal. A 1, 2 equals A21, which equals 0. A 1, 3 equals A31, which equals 0. And A2, 3 equals A32, which equals 0. So every off-diagonal entry is forced to vanish. Only the diagonal entries A11, A22, and A33 survive. The result is a clean diagonal matrix. Therefore, S intersect U is exactly the set of 3x3 diagonal matrices, and the dimension of S intersect U equals 3. We have two 6-dimensional subspaces inside a 9-dimensional space. A natural attempt to combine them would be to take S union U, that is every matrix that is symmetric or upper triangular. But watch what happens. Take this symmetric matrix S, row 1 is 0, 1, 0, row 2 is 1, 0, 0, row 3 is 0, 0, 0. You can check it's symmetric because entry row 1 column 2 equals entry row 2 column 1 and so on. Now take this upper triangular matrix U, row 1 is 0, 0, 0, row 2 is 0, 0, 1, row 3 is 0, 0, 0. Everything below the diagonal is 0, so it is indeed upper triangular. Both of these matrices live in S union U. Now add them. S plus U gives row 1, 0, 1, 0, row 2, 1, 0, 1, row 3, 0, 0, 0. Let's check. Is this sum symmetric? Look at entry row 2, column 3, it equals 1. But entry row 3, column 2 equals 0. Those are not equal, so the sum is not symmetric. Is it upper triangular? Look at entry row 2, column 1, it equals 1. That's not 0, so it's not upper triangular either. The sum has escaped the union. S plus U is not in S and it's not in U, so it's not in S union U. This means S union U is not closed under addition, and therefore it is not a subspace. This is exactly the same idea as two lines through the origin in R2. Each line by itself is a subspace, but their union is not. You can add a vector from one line to a vector from the other, and the result lands off both lines. The correct construction is the sum of subspaces. S plus U is defined as the set of all S plus U, where S belongs to capital S and U belongs to capital U. This always produces a valid subspace. Now here is the key claim. S plus U equals all of M. Let's prove it with a concrete example that illustrates the general method. Take any 3x3 matrix A, say A equals 2, 3, 5 in the first row, 1, 4, 7 in the second row, and 6, 8, 9 in the third row. We build a symmetric matrix S as follows. Copy A's entries on and below the diagonal, then mirror them above the diagonal. So S gets the diagonal entries 2, 4, 9. Below the diagonal, we copy 1, 6, and 8. Then we mirror these above the diagonal, giving S equals 2, 1, 6 in the first row, 1, 4, 8 in the second row, and 6, 8, 9 in the third row. This matrix is symmetric. Now define U as A minus S. Computing entry by entry, the first row gives 0, 2, negative 1. The second row gives 0, 0, negative 1. The third row gives 0, 0, 0. Notice that U has all zeros below the diagonal, so U is upper triangular. Let's verify. A equals S plus U. Adding the symmetric matrix and the upper triangular matrix recovers our original A. This construction works for any 3x3 matrix, not just this example. Every matrix in M can be decomposed as a symmetric matrix plus an upper triangular matrix. Therefore, S plus U equals M, and the dimension of S plus U equals 9. Now the payoff. The dimension formula for subspaces states the dimension of S plus the dimension of U equals the dimension of S intersect U plus the dimension of S plus U. Let's plug in our numbers. The dimension of S is 6. The dimension of U is 6. The dimension of S intersect U, the diagonal matrices, is 3. And the dimension of S plus U, which is all of M, is 9. So the left side gives us 6 plus 6, which equals 12. The right side gives us 3 plus 9, which also equals 12. It balances perfectly. This formula mirrors inclusion-exclusion from combinatorics. For finite sets, the size of A plus the size of B equals the size of A intersect B plus the size of A union B. The logic is the same. When you add the dimensions of two subspaces, the overlap gets double counted, once in each subspace. The formula corrects for that by adding back the intersection on the other side. Dimensions of subspaces aren't independent, they're linked by a conservation law. This formula works for any two subspaces of any vector space, not just matrices, polynomial spaces, function spaces, any structure satisfying the vector space axioms. Vector spaces aren't about what the objects look like. Arrows, matrices, polynomials, functions, these are all different costumes. What matters is closure under addition and scalar multiplication. Once those axioms hold, every theorem applies universally. Let's see the full picture for our example. The outermost space is M, the space of all 3 by 3 matrices with dimension 9. Inside it, we have two large overlapping subspaces, S, the symmetric matrices, with dimension 6, and U, the upper triangular matrices, also with dimension 6. Their sum, S plus U, fills all of M, and their intersection, D, the diagonal matrices, sits right in the center with dimension 3. The containment relationships are clear. D is contained in S, which is contained in M, and the D is also contained in U, which is contained in M. The dimension formula confirms everything balances. 6 plus 6 equals 3 plus 9. 12 equals 12. Check. The dimension formula tells us that two subspaces can't overlap and combine arbitrarily. If you know any three of the four quantities, dim S, dim U, dim of their intersection, and dim of their sum, then the fourth is forced. This same principle reappears in the rank nullity theorem and throughout abstract algebra. Subspaces have a budget, and it always balances.